In this video, I would like to give you an introduction to gravitational potential energy. Now, potential energy is really a stored energy. So gravitational potential energy is the stored energy due to an object being located in some gravitational field. Let me give you an example. Welcome to our video on gravitational potential energy. Potential energy is really just a stored energy. Gravitational potential energy would be the stored energy that is associated with the position in the gravitational field. Suppose you lift some object, rock for example, with a mass m measured in kilograms to some vertical height, delta y, which I'll relabel as h, within some uniform gravitational field, which I've shown with these red arrows, which represents the gravitational field. Gravitational field, by the way, has a magnitude of 9.8 meters per second squared downwards when you're near the surface of the Earth. So if you were to lift this object from this initial position to this final position, you'd have to perform work to move the object to the new location. The work done by you would be equivalent to the change in potential energy, the gravitational potential energy, which is equivalent to the mass multiplied by the acceleration due to gravity multiplied by the height. This formula is located on your AP formula sheet. Delta U, by the way, represents change, and U stands for stored energy, and the little subscript G is to remind you that's a stored gravitational potential energy change. If we talk about the SI units for a moment, the mass is measured in kilograms, the acceleration due to gravity is measured in meters per second squared, and the height that it's moved is measured in meters. So that would give you units of kilograms times meters squared all over second squared. And in an earlier video, I showed you that was equivalent to a joule. So back to our example. If you were to lift this mass upwards, the potential energy would increase. See, there is more potential energy at higher elevations than there is at lower elevations. If you were to think of this as a stone that you were to throw, say, upwards in the air, with some initial vertical velocity, a mass m, you would have a lot of kinetic energy at this point. And then as the stone would start to rise, that velocity would start to decrease until it gets to the very top of its path, and the velocity would be zero momentarily. At this point, the kinetic energy would be zero. And that loss of kinetic energy would be equal to the gain in gravitational potential energy. And then as the stone then starts to fall back downwards, then the kinetic energy would now start to increase as it moves back downwards. You'd have velocity downwards, and then as you get down to the very bottom, you would get the same amount of kinetic energy that you had when you threw it up, and you would lose the same amount of potential energy as the kinetic energy that was gained. An important thing to realize is that this holds true not only for objects that are thrown vertically straight up and come back down, but also would work if you were to follow into a projectile path, or even a roller coaster, as you'll see in the future examples. Below the given formula, we have a short derivation for how the gravitational potential energy formula came about. So let's consider you take that object with mass m and you were to lift it up with your hand. So you have your hand here pushing upwards with a force, and you were to push it up at a constant velocity as it moves upwards. So why am I choosing to do a constant velocity? Because I don't want to have any changes in kinetic energy. And so therefore, really all we're going to get is a change in potential energy. Now, the work that you would do in lifting this object straight up would be given as this formula over here. Well, in general, by the way, work is force times displacement times the cosine of the angle between the force and the displacement. So if you're looking at the work done by you, your hand, your force would be pointing upwards and the displacement would be upwards. So therefore, the cosine of the angle would be actually 0 degrees, which is just 1. So this would disappear and you would just get force times displacement. Now, since the object here, let's say this is our mass here, is moving up at a constant velocity, that would mean that the acceleration would be 0, and the sum of the forces acting on it would be 0. So the upward force by your hand would be equivalent to the force of gravity pointing downwards. So F would be really equal to just simply Fg, which is equal to the weight of the object, which is mass times gravity. So now if we substitute F with mg now, and then replace the displacement with just simply h, we end up with the formula mgh. So the work done by you in lifting this up would be equivalent to the mass times acceleration due to gravity times the height h. So when the object moves upwards, the gravitational potential energy increases, as we mentioned earlier. But this is interesting. Let's talk about signs for a moment. The work done by the gravitational force would actually be negative. And this confuses people quite often. You see, the force of gravity is acting straight down, but then the displacement would be straight up. And the force of gravity is down, and so the angle between the displacement and the force of gravity would be actually 180 degrees. And so if we were to calculate the work done by the force of gravity, I'll just write work grav for gravity, it would be the force of gravity multiplied by the displacement multiplied by the angle between the displacement and the force of gravity, which would be 180 degrees. And the cosine of 180 degrees is -1. And so you end up with negative mgh. So although the potential energy increases on the way up, the work done by gravity is actually negative. So in general, the work done by gravity is just really equal to the negative change in gravitational potential energy. But the work done by your hand that's pushing it upwards would actually be equal to the positive amount of potential energy. So if I wrote work done, say, external, that would be equal to the positive change in potential energy. So when it rises, you have an increase in potential energy, and you have a negative work done by gravitational force. And when the stone falls downwards, there is a decrease in potential energy as you go from more potential energy to less potential energy, but the work done by the gravitational force is actually positive. I can see how people often confuse this with signs. So I always find that it's best to think of your general definition of work, which is force times displacement times the cosine of the angle between the force vector and the displacement vector. So if you're looking at the work done by the external force, which is in the same direction that it's moving in this particular case when it moves upwards, then the work done is positive. But if you're looking at the work done by the force of gravity, which is straight down while the object is moving upwards, then the angle between these two vectors is actually 180 degrees, which leads to a negative work being done. You can probably even use the analogy of money. Think of potential energy like storing money in the bank. So when you move the object upwards, it's like taking your money and putting it into the bank account. And when the object moves down, then the potential energy decreases, and that would be like withdrawing your money out of the bank account. The action of spending your money, which is really doing work, would be positive when it falls down. Anyway, go ahead and try the next few examples that deal with gravitational potential energy and also kinetic energy.